All right, so as we're looking at geometric sequences, one of the things to understand is we're looking at how numbers progress still, but here they're progressing in a different way. Does anyone recall from previous study maybe how a geometric sequence will change?
Their factor is the same. Or like you multiply it by the same. Yeah.
Okay, yeah, we're multiplying by the same thing every time. Okay, we're multiplying by the same thing. If we look at this, I want to do kind of a similar thing to what we did with our arithmetic. Let's say we have this sequence 3, 12, 48, 192, 768. All right. If we were to graph this, okay, we have, whoa, there we go. We have 1, 3, 2, 12. I'm going to 2, 3, 4, and 5. Now we have to go really, really high evidently here, so you know, the 0.13 we'll put really low. And then 212, that's going to be a little bit higher. And then 348, that's going to be quite a bit higher. And then 192, that's going to be here. And then 700 something is way, way up here. Okay, so you'll notice here, our graph is clearly not linear. In fact, if you were to try to connect the dots here, what would this graph look like actually? What? Okay, kind of looks like half of a parabola. Do we know any other functions that kind of look that way?
Exponential.
There we go, the exponential, okay? Good, the exponential. So our graph, what we're talking about here is something where our terms in our sequence are going to grow exponentially or possibly shrink exponentially. Okay? Now, anytime you've got this exponential type of growth, remember these were the functions y equals a times b to the x. Okay? And the key was we had something being raised to a power. Okay? Now these may not be quite as familiar as dealing with lines, but if you think of geometric sequences as exponentials, then the same principles that you learned back when you were working with exponentials will apply here. Okay? Now, the key here is recognizing the common ratio. The common ratio R is that thing that's going to be raised to a power. Okay? Instead of y's and ab's and x's, we have a sub n equals a sub 1 times r to the n minus 1 power. That's our formula here. The common ratio is that value of r, and that's how much the term is going to be multiplied by to get from the term you're at to the next term. Okay? In our example here, what is our common ratio?
4.
Yeah, 4. Okay? If you're trying to figure that out, make sure you always divide 1 by the one before it. Okay? So r is going to be 12 over 3, or you could do 48 over 12, or 192 over 48, or even 768 over 192. No matter what terms you use, if you divide them like that, you'll get the common ratio 4. Okay? Now we'll draw some comparisons here with the exponential even more as we move forward. Okay? But you can even see the comparison right now with just the form of the definition of these sequences, okay? Now, if we're trying to write a geometric sequence, of course we've already looked at it and we can tell that it is in fact geometric. One of the first thing you need to do is figure out what R is, okay? What is that common ratio? Then, R is the base of the exponential. Notice I have copied here again that formula that we just saw. R is the base of the exponential part, okay? Notice a sub 1 is being multiplied by r to a power, okay? So r is the base. And then, of course, simplify. Now, this is one step that students often will forget to do, okay? But it is important to make your answer, make sense to someone who's just looking at it for the first time. Okay? So, for example, on the previous example that we had that 3, 12, 48, 192, and so on. Okay? If I'm trying to find that, first of all, we already saw that r is 4. So I know that my formula is going to be a sub n equals a sub 1 times 4 to the n minus 1 power. Okay? Now what is a sub 1 here? It's that first term. It's 3. Okay? So I have 3 times 4 to the n minus 1 power. Now you might be saying at this point, okay, what am I simplifying? What do you mean by simplify? Alright? We have 4 to an n minus 1 power. And we'd like to avoid having to, deal with an n minus 1 power. It'd be nice to just be able to plug in values of n and it, we can figure out our answer a little simpler. Okay? If we look at this, though, what could I do with that 4 to the n minus 1 power?
Go log on both sides.
Yeah, we could. Let's not. But that wouldn't be wrong. There's a little simpler way. I just want to end up with a sub n equaling something with 4 to the n power. I gotta fill in some more gaps here, but what can we do?
Oh, wait. I don't know. 1/3? 1/3. No, I have one more. Never mind.
Oops, that should be a sub n. If I want it to be 4 to the n, could I multiply this by something? Somehow split this up? What? Aha, look. Remember when you're multiplying things that have the same base? You add the exponents together? So n plus a negative 1 would be n minus 1. Is that making sense?
Yeah.
Okay. And then 4 to the negative 1 power is what?
Oh, 1/4.
It's 1/4. That's right. Okay. So I could rewrite this as 3 times 4 to the n times 1/4. Okay. And now we're doing exactly what Jason, right? Exactly what Jason said. We're dividing by 4. So it's 3/4 times 4 to the n. Okay? Now, once you get the hang of this, you could probably just jump from where we are at to your final answer right away. Because you'll notice every time the way you get rid of that negative 1 power is you're ending up just dividing by r. Okay? Yes? Sam?
Will our answer be wrong if we do it the first way?
It just won't be complete. It's obviously not wrong, but I'd like you to finish it out go this last step, because in reality, and as we look at applications later on, this is the form you're going to see. Okay? For example, one application is like compound interest. You know, you're going to see something just to the n power, the x power, or whatever. You're not going to have that n minus 1 there. So it helps us see a little more intuitively where the formulas come from and so forth. Okay? So, not wrong, but this is our best answer. Okay? Now, here's where the problem solving comes in. You guys have done a little bit with geometric sequences in the past, all right? So really nothing that we've talked about is totally new. What can be a challenge here is figuring out something like this, okay? We're given two terms of a sequence, and we know which terms they are, and we know that it is geometric. But now we want to figure out another term, all right? So let's say we have the fourth term of a geometric sequence is 125. So I'm actually going to write that down. A sub 4 is 125. And then it says the 10th term. So that's A sub 10, right? Equals 125 over 64. Okay. Now, how might I go about figuring out what the 14th term might be? What are some things I have to figure out,
You
Ben?
could put them in the same equation and then set two variables equal to each other.
Okay, how might I do that?
You could do a sub the same equation that we did before, where I had the n minus 1 in the numerator, in the exponent.
Okay, so like using this form?
Yeah, no, but then you're missing the no.
What do you miss?
You're missing the r.
Okay, well, we are missing the R, and that's the key. Okay, we're missing the R. Maria, can you help us?
Could you use them as like points?
Okay,
Or 125 and then 10, 125 and 60.
you absolutely can use them as points. What were you gonna say, Jacob?
Yeah, remember this last year we did this thing where we like changed like the ace of 4 to be like an ace of 1 and then sort of solve from there.
Okay,
Just use this one to divide this four to get R.
I think you guys are on the right track. You guys have some good ideas. Neef, what do you think?
I remember for arithmetic, you like if they give you two terms, you subtract them. I think for like geometric, once you divide them.
Okay, when you were finding slope, you're right. You subtracted the y coordinates, and then you subtracted the x coordinates, and you put those in a ratio
Yeah.
for slope. Okay, you can do a similar idea here if you're dividing. Okay, you do have to make sure that you get the right ones on top. All right. Did you figure out what you were gonna say, or
Yeah.
what?
I'm thinking which one should be.
Oh, okay. So let's say if we were to divide
10 over the fourth term.
divide the 10th term, which is this, divided by the 4th term. Okay? What does that come out to? 1 over 64. Yeah. Okay? So that's the 10th term divided by the 4th term, right? So what would I do with that?
Doesn't that give you the, what's it called? The R?
Does that give us the R? A sub 10.
Would you have 2 points next to each
Yeah,
other?
yeah.
Like 3 and 4.
Okay,
Yeah.
here's the deal. You don't have to. You have to have them right next to each other if you want it to give you R right away. There is a way to get R from this, though.
But we know you can just A4 become A1 and A10 become A6.
You can. You'd still have to do the same next step if you did that. No?
It would do the square root. It would do the square root.
Oh, we're right. You're right on the right track. Okay.
6.
The what?
6.
Why the sixth root and not just the square root?
6.
Oh, 6 squares in between.
No, 10 minus 4.
Yeah.
Okay, yeah, look. How many steps? Remember how a geometric sequence works. A geometric sequence works because you have a sub 4 and then the a sub 5 is simply a sub 4 times r, right? Right? And then every step I have to multiply by another r. Okay? And now we get to a sub 4 times r to the 6th. That is a sub 10, right? So how do we get from a sub 4 to a sub 10? You've got to multiply by r to the 6th. Okay? So if you divide a sub 10 by a sub 4, guess what that equals?
R to the 6.
R to the 6th. Okay?
Just 2.
So count, you just have to know how many steps does it take to get from one term to the other. It's going to take 6 steps.
1 over 2.
Okay? Yeah.
And then once you plug it into the A4 and you figure out what your A1 is.
If we actually don't necessarily have to. Watch this here. 6 steps. Just to back up for a second. 6 steps means we multiplied by an r to the 6th. Okay? To get from a to the 4th to a to the 10th. So when we divide this thing, like we did, we know that this is r to the 6th. So that means r is the 6th root of 164, which happens to be 1/2. Okay? Now technically it could be negative 1/2. That's why I assume that all the terms are positive. Okay?
Yeah, because you're only doing the even term, so we don't know if it's going positive or negative on that.
Yeah. So now, how could we get the 14th term at this point?
Without finding the first term?
No, we can
Or
base
with-
on
However you want.
based on 10.
What could we do if you started with the 10th?
Okay, you say a sub 14 equal a sub 10 times 1 over 2 parentheses 3 on the top.
Close. A sub 14 would equal a sub 10 times that r to what power?
Is it?
No.
Or
To the 4th. Yeah. You have to take 4 steps to get from 10 to 14. So you'd have to multiply by 1/2 4 times. Okay? So actually you don't necessarily have to go back and get a sub 1. You can if you want, but you don't have to. You just need to multiply by that r 4 more times to go 4 more steps down the sequence. Okay? And then that ends up being something.
125 over 64 times 116.
64 times 16.
Yeah.
256 is it 1028?
24.
Yeah, it is.
1024.
Yeah.
1024. Okay. All right. So that right there is our answer.
Wait,
Okay.
for the 1024, did you get it by like, the half to the fourth and then you just add, like, multiplied it times the 64?
Yes.
Okay.
Yes. Yeah, the 2 to the fourth is 16. 64 times 16 would give you a 1024.
Right. If it was, would it be faster, let's say if it was asking for the 80th term, would it be faster to find the first term or just to do r to the 70th?
If you've got a calculator, it probably doesn't matter. If you're doing it by hand, then it might be useful to like find your a sub n in general and then plug in 80. So, kind of depends on what tools you got. Okay? So, just to kind of recap this whole process here. If you get the ratio of, I always do the term with the higher n over the term with the smaller n. Okay? That ratio there will equal r to a power. And the power is going to be however many steps it took, or however many steps are in between the two terms you know. Okay? All right. Now, as we did with arithmetic, we want to look at sums. Okay? We want to look at sums. You'll notice there's a formula here that we're given for the sum of a finite geometric sequence. Now, here's a little tip. Let's say you forget the formula. Okay? You forget the formula how to do this. Or maybe you don't even recognize it as a geometric. You can always just figure out each term and add them up. Alright? Don't forget that. In fact, you may even get one where I give it to you. I give you something in sigma notation and it's not arithmetic and it's not geometric. Don't use one of the formulas for that because it won't work. Okay, in that case you just have to plug it in. Alright, but in this case, notice we have the sum from n equals 1 to 12 of 4 times 0.3 to the n. Okay? Now what here tells us that we are adding up terms of a geometric sequence?
To the n.
Alright, we see it to the nth power. Okay? Now in that case, what does r equal?
0.2.
Okay? Remember, r is always the number that's being raised to that power. So r is 0.3. Okay? Is everyone with us so far? Okay. Alright, so notice our formula here. Our formula says that the sum from I equals 1 to n, this is important here, I equals 1 to n will equal a sub 1 times 1 minus r to the n over 1 minus r. Okay? So notice we are starting at 1 in this case. So I first of all need to find a sub 1. Okay, well what's a sub 1?
1.2.
Okay, if we plug that in, 4 times 0.3 to the first is 1.2. Okay? Now the other thing I need is n for my formula. What's n in this case?
12.
Alright? It's 12. By the way, what's some other notation that we could use for this whole sum? Some other notation you might see. How about S sub 12? This is the 12th partial sum of the geometric sequence. Okay, that term still applies here. We could say that this is the 12th partial sum. All right. So, go ahead and try plugging that in and see if you can get the right value. Okay, now that we've identified all the key parts, what would S sub 12 equal? Okay. You can use your calculator if you need, but give it a shot. That's why they have those cases.
Yep.
All right, so we set this up. We've got our a sub 1, that's 1.2. We have a 1 minus 0.3 to the 12th power over 1 minus 0.3. Okay? One little tip, by the way, if you're plugging this into your calculator, is do what you can in your head. All right? You are all capable of subtracting 1 minus 0.3 in your head. All you do when you don't do it in your head is give yourself room to make a mistake punching it in. All right? So, we have this here. Let me move this. Oop. Not that. Yeah. Nope, wrong thing. So that denominator would be, 0.7. Okay, so what do we end up getting here?
1.714. Oh wait, yeah, okay, yeah, 1.714.
1.715?
Yeah.
Okay. Is anyone not getting that? Not sure what you're doing wrong? All right, good. So here's the question. Our formula says this is for when we have the sum from I equals 1 to something. So what if it doesn't start at 1?
Equals
Can you add the 13?
Maybe see one more.
This one starts at 0.
AY equals 0.
Well, here's the thing. A sub 1 is still going to be the value of n, so, but this one has an a sub 0, you could call it.
What does that mean?
It just means, what's the value of this when n equals 0?
4.
It would be 4, right? So if I had 4, that's going to give me just 4. But I need to add to that the rest of it, right? What is the rest of it?
You're gonna do, since when n equals 1, it's gonna be 11, right, so, no?
No. Think about it. Right now, we did when n is 0, so what do we have left? We have the sum from n equals 1 to 12 of 4 times 0.3 to the n. Well, how do we get that?
Use the 7.
What's that?
Use the 7.
Didn't we already do it?
What, Sam?
We already did it.
We already did that, right? We already did the sum from 1 to 12. Okay? So here's the deal. Our formula calls for us to go from 1 to n. If for some reason it doesn't start there, you can still use that formula for most of your answer. Just figure out how to get what more you need, okay? We just did S sub 12. Up here, it's 1.715. So our total is 5.715. Okay? That's the sum. What if it went from n equals 2 to 12?
A sub 1.
Yeah, you could use your previous answer and just subtract a sub 1. Okay? So, this formula is really useful. You could even do this. Let's say you wanted to find the sum of let's say n, that's a little redundant. I don't need that. The sum from n equals 20 to 25. Okay? If I want the sum from 20 to 25, what could I do? Using my formula I already got.
Use the S sub 6.
No.
Can we just A sub 20 become A sub 1, which is saturation? Understand that A sub 25 become A sub 5?
That is one way you could think of it. Now, if you went from if you made a sub 20 into a sub 1, you'd have to go up to 6. Because you'd count 20, 21, 22, 23, 24, 25. So you could adjust to like your whole scale of n's that way. There's another way you could do it as well. What if I found s sub 25? That includes too much, right? What don't I want?
1 to 19.
1 to 19. So I would have to subtract
S19.
s sub 19. See how that works?
There's no faster way.
I don't know. With only 6 terms, it might just be faster to figure out the 6 terms and add them up. That's the nice thing, though. You could figure it out a lot of different ways. You can adjust the scale for your n's so that your a sub 20 is now a sub 1. You can do it this way. You can figure out the 6 terms and add them up if you want. It really doesn't matter. There's a lot of different options that you
How
can...
would you adjust the scale?
Okay, what Donald's describing there is saying, okay, originally a sub 1 was 1.2. Okay? So basically what he's doing is saying, okay, I want a sub 1, I want a sub 20 to be my new a sub 1. So basically everything's increased, or I should say decreased 19 spaces. Alright? The one thing that you have to be careful about with that is that a sub 20 was 4 times 0.3 to the 20th.
Mm-hmm.
You need to make sure that when you plug it in here, you're still plugging in this value. As long as you plug in the first value you want here, you can make n into just how many terms you want.
From 20.
From 20.
So 20 to 25 would be 6.
It would be 6 terms, yeah. So you could plug 20 in there and then just plug a 6 in there. It'll give you, starting with a sub 20, it'll give you 6 terms added up.
Oh, I think that's easier.
Okay, yeah, some people like doing that. Some people that just really confuses. So if that makes sense, that's awesome, you know. And again, I don't really care what method you use as long as it's valid, you know, and that's why you guys show your work. Okay? Yes.
How much is about a sub? Okay.
You got it?
Yeah.
Okay. All right, now there's one additional thing that we need to discuss with a geometric series that we didn't really need to discuss with an arithmetic, because in arithmetic the terms were either constantly getting bigger and bigger and bigger, or they're getting smaller and smaller and smaller into the negatives. Okay? So regardless, if I tried to add up an infinite number of terms, I was either going to get positive infinity or negative infinity. That's the only two possible answers if you're adding up an infinite number of terms with an arithmetic. A geometric sequence and series is a little bit different. There actually is a formula, you'll notice here, for the sum of an infinite geometric series. Okay? And you'll notice it's actually the same formula we just had, except, remember, the formula we just had that 1 minus r to the n. Okay? Well, we get rid of that part. And that's our formula for the sum of an infinite geometric series. Okay? Now, this only works in certain cases, though. It only works if your common ratio has an absolute value less than 1. Okay? Now, think about that for a second. What's going to be happening to the terms of the sequence if the absolute value of r is less than 1? Okay, the value of a sub n is going to be getting smaller. In other words, it's going to be getting closer and closer to 0. Okay? Now, this can happen one of two ways. Notice here, if it's a positive value, then our terms will it'll just look like this. It'll look like an exponential decay function. But notice they'll be getting closer and closer and closer to 0. There will be an asymptote there at 0, but it'll continue to get closer and closer to 0. Okay? If r is negative, it'll still get closer to 0, but watch what happens. You'll have that one, but then this will jump down to the negatives. And then you'll have this one, but this one will be down here, and then this. And you'll see it bouncing back and forth, back and forth, back and forth on either side of that x-axis, on either side of 0. Okay? But it'll still be getting closer and closer and closer to 0. Alright, and there's actually a concept called the limit that we deal with. The limit of the values of that sequence equals 0.
It never
Alright.
touches it.
It never actually touches it.
But you know.
A limit is a value it's approaching,
Yeah.
and it doesn't have to touch. We're actually going to have a unit on limits at the end of the year. Okay, but here's the concept behind why we can actually get this formula. Okay? So, notice here in this case, we have r equal to 0.6. Okay? So, notice our formula is the sum from I equals 0 to infinity. Okay? So this formula here, or this problem here, starts at n equals 1, right? So we actually are going to have, if we use the formula, we're going to have one too many terms, right? So I'm going to do the sum from n equals 0 to infinity. And then I need to subtract that term where it equals 0, right? So that's going to be 4 times 0.6 to the 0 minus 1. Okay? So be careful with our formula here. The formula goes from I equals 0 to infinity. In this problem, we went from 1 to infinity. Okay? So notice here, let's use our formula. What would a sub 1 equal? 4 times 0.6 to what power?
0.
To the 0. So it would just be 4. Okay? So that's my numerator. 4 over 1 minus.
0.1 over 0 at 4 over 0.4.
Yeah, okay. So this is going to be 4 over 0.4. Okay? Now we need to subtract though. We subtract 4 times 0.6 to the negative 1, right? So that's going to be a minus 4 over 0.6.
Wait, how did you get the 1 minus 0.6 on the grade?
This bottom part of our formula is 1 minus r.
Oh,
Okay? It's alright.
5 over 3.
What'd you get?
5 over 3.
Oh, you're just talking about the 0.6 to the negative 1? Okay. Yeah, that's 5/3. Okay. So you could rewrite that. What do you end up getting though with this? What do we get? 10 minus 6 2/3. Okay, that'd be 3 1/3.
Wait, how did you get 10?
If you made that 40 over 4,
Let's just see this one.
10. Okay. So yeah, 3 1/3 would be our final sum.
Can I write 3 over 10? 10 over 3?
Yeah, 10 over 3 is fine. Okay. Yes.
If you have like n equals like 5, for example, on the bottom, you would just do the equation that we did on the left part of that, and then just say minus and then plug in n equals 5, rather than n equals 1.
You're talking about like right here, if it were the sum from n equals 5?
Yeah, like that.
In that case, you could still do this, except instead of subtracting, you would need to add the partial sum. Or, I'm sorry, you would need to subtract the partial sum from 0 to 4.
Okay. Yeah, because you're not including. Okay.
Yeah.
Okay.
Now, some of the geometric sequences or series are a little easier to work with. What's the sum for the last one?
3.3.
Yeah, notice it's 3 tenths, 3 100ths, 3 thousandths, and so on. That's going to be 3 1/3. Okay? We could do that using this formula. If you think about it, the sum is, what's the first term in the sequence? 3. What's R? What's R here?
1/10.
1/10. So 3 over 1 minus 1/10 would be 3 over 9/10, which would end up being 30 over 9, which happens to be 3 1/3. Okay? Yes?
Wait, I'm trying to go back to it, but I'm still confused on how you got the 10. in
That's
the
okay.
last one.
On that one, if you have 4 over 0.4, if I multiply the numerator and denominator both by 10, does that make sense?
Yeah.
You'd have 40 divided by 4 instead of 4 divided by 4/10. All right, any questions, comments, anything? Yes?
Are they ever gonna make it so like you have to find a sum of like 5 to infinity?
Possibly, but that's kind of what Ben was asking about. If you want 5 to infinity, you can just do,
You just minus it by the
you could just do the sum from 0 to infinity. Get rid of that actually. Do the sum from n equals 0 to infinity, and then just subtract the sum from n equals 1 to 4, if you want the sum from 5 to infinity. And I know that's terrible notation, but you get the idea. Actually, that should be 0 to 4. Okay? Alright, so we're not going to mess with the increasing annuity at this point. I gave you some to practice with. Again, you've got the required IP. This is more than just the required. Give those a try. I was hoping to do this in class a little bit, but we didn't have time to. Give those required IP a try. We'll start with that on Tuesday, okay? Or on Thursday. Today is Tuesday. All right.